Hey guys, welcome to Unit 3, Lesson 1. This is on sampling distributions and the central limit theorem. You can see this picture that I drew up in the top right is just about how to take a sample, which is what we've been over in the past. The first part of this is just going to be basically a review. So sampling. We often cannot test out a whole population when we want to look at something, so we'll test a random sample of the population. Right? And we've done that. And back in Unit 1, you remember sampling and like the different ways to sample, random and stratified and cluster and everything like that. Okay, and so the second definition we have, and this is going to be new for you, is going to be sampling distribution. And so this would be if we took every one of the possible samples of a certain size from a population, and then we calculate the mean for each of the samples, and then we graph the results. And so our sample mean, we are going to call X bar. And then our sample standard deviation is going to be an S. And then you can either put this X as a subscript there, or you don't have to do that. I like to put that there so it reminds me what I'm working with. And then standard error is it measures the sampling variability of X bar. And so remember, X bar is our sample mean. And so our standard error is calculated with the sample standard deviation over the square root of n, and if we remember, n is our sample size, and we've used that before. Okay, and central limit theorem, so it's a big word, but don't get overwhelmed by it, it's not too hard. Central limit theorem is for sample sizes that are n is greater than or equal to 30, so that's just saying sample size is greater than 30, or 30 or greater. The sampling distribution is approximated by a normal model. If the population is already normal, sample size doesn't matter. So if by chance the population that you're sampling is already normal, you could take samples of whatever size and it will still be a normal sampling distribution. Okay, and so now if we were working with a sample proportion, then we would use p hat, and then we would still use S for our sample standard deviation. What we would do here is we would say standard deviation of our sample proportion. So the standard deviation of those proportions would be this formula right here. So it's the square root of p times 1 minus p over n. And remember, n is our sample size, and p is the proportion that they give us in the problem, or the population proportion. And again, up here back in definition 7, the sample proportion, it has to be a value between 0 and 1, and that's for any proportion. So that's how you know if you're working with a proportion or not, is if your value is between 0 and 1, you're more often than not going to be working with a proportion. So for number 9, the central limit theorem for proportions says that the distribution, or the sampling distribution of proportions, is approximately normal if at least 10 successes and 10 failures are expected for the sample size. And remember, our NP is how we determine successes, and our n times 1 minus p would be how we determine our failures. All right, let's start working some problems. So we're going to come here, and first problem says, let x be the lifetime of an electronic device. It is known that the average lifetime of the device is 787 days, and the standard deviation is 132 days. Let x bar be the sample mean of the lifetimes of 192 devices. The distribution of x is unknown. However, the distribution of x bar should be approximately normal according to the central limit theorem. Calculate the following probabilities. And remember here, so for central limit theorem, this 192 devices is greater than 30. So we know that that's why it's central limit theorem. And let's see, so it says the average lifetime of the device is 787 days, and that's the population. And so when we take samples of whatever size, the sample mean is usually equal to our population mean. So our x bar is going to be 787, and then if we want to find our standard error, then we can do, let's see, so it would be, what was the formula for that? It was the standard deviation over the square root of n, so 192. And remember, n equals 192. And so then we would calculate this, and this is equal to 9.526. And so we've got our two important statistics for this sampling distribution. And so what we would do here is we would have to do this on RStudio, but I'm not going to do it on RStudio. I'm just going to write down the command for you. So it's pnorm, and then the first thing you would do is you would put this value right here. So it would go 774, and then a comma, and then our mean that we're looking at, so 787, and then our standard deviation for this problem, which would be the standard error, and then it would be 9.526. So that's going to give you our answer for the first one, and that answer for the first one is 0.0862. Okay, and so remember on RStudio, the way it gives it to you is when you use pnorm. So this command pnorm right here will give you all the proportion to the left of the value that you enter on the first spot. So for the next problem, when it gives me x is greater than or equal to 800, we're going to have to do something else, because if I just put 800 in there, then it's going to give me all the values to the left of 800. Well, we want the values to the right of it for a greater than or equal to. So we would have to do 1 minus pnorm of 800, 787, 9.526. And so if you can see this, that 774 and 800 are the same distance away from the middle, and since our normal distribution is symmetric, since it's asking for less than the value on the left and greater than the value on the right, the probability of both of those is going to be the same. So this one is going to be 0.862. So let's see, we have our normal graph down at the bottom, and I'm just going to go ahead and fill it in. So 787 would be there, and then you would add the standard error to get over here, would be about 796.5, and then on this side we would be at 777.5. So what I did there is I subtracted and added 9.5 to both sides, for that's the standard error for our sampling distribution. And then our sampling distribution is normal because we took over 30 trials. And so for A in this problem, it would be right around here, so it would be 774, and then B in this problem would be 800, so it would be right around here. And if you can see, this area less than 774 and this area greater than 800, they're going to be the same, right? Because it's symmetric. So that's why we can flip those around and do that. And so for this next part, it wants the probability of greater than 769 and less than 801. So 769 is going to be somewhere right around here, and then 801 is going to be somewhere right around here. So we need all this area inside those two. Okay, so what we would do here is we would say pnorm of 801 and then 787, 9.526. So that gives us, right, that gives us all this area to the left of that first value that we enter. And then we would have to subtract all of this area to the left of 769. So it would be pnorm of that minus pnorm of 769, 787, 9.526. All right, and that is going to give us 0.8998. And if we remember our empirical rule, which was the 68, 95, 99.7 rule, about 90% of the data here is in between these two values, and that looks about right because we have our one standard deviation here, and then we have our one standard deviation to the left there. And if you go a little bit further and you stay a little bit further in from the 95, between 68 and 95, closer to the 95, gives us our 90% there. So logically, if we think that one through, it does sort of work out. Okay, the next problem. In 2009, the FDA Oncology Drug Advisory Committee recommended that the drug Avastin be approved for use in glioblastoma, a form of brain cancer. Tumor shrinkage after taking a drug is called a response. Historically, response probabilities for brain cancer drugs are approximately 0.05 or about 5%. So if I was working this problem, immediately I would write down P or P hat because we're doing samples. So P hat is 0.05 for this one because the sample proportion and the population proportion are the same. So based on historical results, if a random sample of 250 individuals using Avastin is collected, how many successes should we expect? And remember, what we do for successes is 250, which is our N, multiplied by our P hat, so 0.05. And so this would give us, let's see, this would give us 12.5. So the next part says, what is the probability rounded to 3 decimal places of the number of successes? And if you remember back, I think it was our last lesson, where when it's a discrete variable, you could have 1 success, 2 success, 3 success, 4 success, all the way up to 250 in this one, right? Because you can't have a half a success. So the probability of getting 12.5 successes is 0 here. Because you can't have a half success for this trial, but that's the expected value. And so the probability of the expected value is 0 for this problem. Okay. Next problem says the triglyceride levels for the residents of an assisted living facility are recorded. The levels are normally distributed with a mean of 200 and a standard deviation of 50. If samples of 35 randomly selected residents are taken and the average triglyceride for the sample is recorded, between what 2 values should 95% of all the sample means fall according to the empirical rule? And so remember, our empirical rule was the 68, 95, 99.7, so 68, 95, 99.7, and that means the first standard deviation, so 68% is between these two, and then 95% is between these two, and then 99.5% is between these two. So we have 1 standard deviation, 2 standard deviations, and then 3 standard deviations. So that means 95% of the data falls between 2 values. That means we're taking 2 standard deviations to the right side, 2 standard deviations to the left side for this problem. Okay, and so our standard error in this problem, which is what we need to find because we're taking samples, and so our N, let's identify that first, so N is 35, and then the population standard deviation is 50, so in order to find the standard error, we take that divided by square root of 35, and let's get that, is 8.45, so 8.45. So that means to do this, we would take our x bar, and remember this is the same as the population mean, so x bar is 200. We would subtract it twice, and then we would add the standard error twice to it in order to get our lower value and our upper value. So for this, we are going to find 200 minus 8.45 minus 8.45 is 183.1, and then if we add 8.45 twice to it, we are left with 216.9. So that makes sense for that problem. We basically found the 2 values that 95% of all of our sample means are between. So that would be called, that's sometimes referred to as a confidence level. So we would be 95% confident that the sample mean would be between those 2 values. But we'll get into that in a later lesson, so I'm not going to go too deep into that. So the next problem. In a population of 210 women, the heights of the women are normally distributed with a mean of 64.4 inches and a standard deviation of 2.9 inches. If 36 women are selected at random, find the mean and standard deviation of the population of sample means. And so now if we get here, we know automatically n equals 36, right? And then let's see. So it asks for mu x bar, which is how they're going to write it in this problem, but I would normally write this as just x bar. And if you remember, this is the same thing as the population mean, so 64.4 0.4 inches. And then it asks for the sample standard deviation, or sigma x bar. And now I would write this as S, or standard error, all the same thing. And if you remember, the formula for that is equal to our population standard deviation, which is 2.9, over the square root of our n, so square root of 36, and this is equal to 0.44 inches. Pretty easy, right? And obviously, if you think about it, this one passes the CLT test, right? Because 36 is greater than or equal to 30. Okay, suppose a random sample of n equals 46 measurements is selected from a population of mean mu equals 65 and a standard deviation of 12. Find the z-score corresponding to a value of x bar equals 68. So z-score, remember, is the measure of how many standard deviations you are away from the middle. So our z-score formula for this is going to be x bar minus mu over standard error. And remember, we have to find our standard error, which is the same thing as sigma of x bar, and it tells us our x bar is 68 and our sigma of the population is 12. So our standard error again equals 12 over square root of n, which is 64. So this is going to be the same thing as 12 over 8. So let's see what that is. So 12 over 8 is equal to 1.5. And then, so we have our standard error, we have our mu for the problem, and then we have our x bar. So we can go ahead and use the z-score formula. So our x bar is 68, and that was our observation value for this problem. And then our mu, our population mean, is 65, and then our standard error is 1.5. And so if we take this, we would go 3 over 1.5, and this is the same thing as 2. Okay, suppose a random sample of n measurements is selected from a binomial population with probability of success p equals 0.35. Given n equals 200, describe the shape and find the mean and the standard deviation of the sampling distribution of the sample proportion p hat. So we need to describe the shape, right? And so remember, our central limit theorem for proportions says we need at least 10 successes and at least 10 failures. So successes would be NP, so 200 times 0.35, and this is the same thing as 70. And then our failures is 200 times 1 minus 0.35, which is 0.65, and this is equal to 130. So that checks out for our central limit theorem, and that says in the first part of this problem, which is describe the shape, this would be normal. Okay, now we have to find the mean and the standard deviation of the sampling distribution of the sample proportion. So our p hat, which is the mean proportion, this is the same as 0.35. So this would be 0.35 multiplied by 200. And actually, no, this is not p hat. So for this one, we are going to find the mean and the standard deviation of the sampling distribution of the proportion. So I'm just going to write mu here because it's just a general mean for this problem. So the mean is always going to be equal to NP, so 200 times 0.35, and we already said that equals 70. And then the sampling distribution, so the standard deviation of the sampling distribution equals the square root of p times 1 minus p over n, and we already have that on our definition sheet, so that would be the square root of 0.35 multiplied by 0.65 over 200, and that is 0.034. All right. So last problem. Suppose a random sample of n measurements is selected from a binomial population with probability of success p equals 0.35. If we take a sample of n equals 500, how many successes should we expect from our sample? And I'm going to add another part to this, and that would be describe the shape. So we're going to need to find, for the central limit theorem, we're going to need to find the successes, we're going to need to find the failures, and then if they're both over 10, it's normal. So 500 times 0.35 equals successes, right? And so this is equal to 175, and then 500 times 0.65 equals the failures, and this is equal to 325. That's right, so both of these are greater than or equal to 10, so CLT holds and normal. Easy enough, right? And that's going to conclude our Unit 3 Lesson 1. Thank you for watching.